This is a short introduction to the topic of reflection. In fact, we focus on Java's introspection. So here's a short intake. Well, basically we start from the simplifying assumption that we can separate programs and data. So programs are programs on one side and data is data on the other side. But obviously programs can be represented as data, and then we may have programs that process data that is in fact representing programs, and we have a name for this. This is called a metaprogram. The activity is called metaprogramming. So in this presentation, I'm going to focus on one important form of metaprogramming, that is reflection. And that refers to the situation that a program examines or modifies its own structure and behavior at runtime. So let's look at a simple example. So this is a piece of Java code without reflection, but we are going to kind of transform it so that we use reflection. So what's going on here? Very simple. We've got a class exemplar, which we instantiate, and then we invoke the method run on the corresponding object. So this is just a program. Now we could turn part of this program into data. Like we could replace the reference to the exemplar class and another reference here to the run method. We could turn them into data. And if we do so, then this program also has to somehow perform lookup operations explicitly to find the class on the grounds of data, describing exemplar, and likewise for the run method. And that's what we do here. So first thing to notice is that the exemplar class is now kind of encoded here as data, and also the run method is encoded as data. In both cases we use strings. Other than that, we use designated classes and methods of the reflection API. So in essence what we do here is, given the string for the class, we ask a class and its static method for name to essentially locate the corresponding class. And what we get in return is we get an instance of the class. This class is responsible for representing Java classes within an application. From that class we can look up the default constructor, and we instantiate a corresponding class for constructors. And we can ask the constructor to construct a new instance. By this we get a regular object, and we happen to know that the type of this object is hello world exemplar. And then we can also look up a method from the class, the run method. And we can invoke the run method where we pass the receiver explicitly as an argument. So this is a simple introspection. We can also look at this code in Eclipse. So here's a collection of reflection examples. Here we have hello world. Let's just execute it. Okay, so we see hello world a few times here. Once without reflection, once with reflection. And this is how we invoke the method without reflection. Okay. And by the way, we can just figure out what the type of the object is, which we know anyway though, because we declared it here. And here is how we do it with reflection, just as we had seen, by finding the class, looking up the constructor, instantiating the class, looking up the method, and invoking it. So here's just a list of typical metaprograms So even just a pretty printer for the Java language would be a metaprogram because it consumes some representation of Java. Or Java compiler would be a more interesting instance of a metaprogram because it would consume a Java code representation and it would produce Java bytecode, and Java bytecode of course corresponds to another kind of program. More interestingly for our purposes, I mean, as we are focusing on reflection, the JUnit framework is a metaprogram. In fact, it involves reflection or introspection because when you execute the JUnit framework, it essentially locates test methods and executes them, to which end it actually uses the Java Reflection API. So here's a summary of the terminology. A metaprogram is a program that manipulates programs. So the manipulated programs, to them we refer as object programs. And basically object programs are like data from the point of view of metaprograms. The language in which metaprograms are written is called the meta language, and the language of object programs is called the object language. And if we face the specific case that a program examines or modifies its own structure and behavior at runtime, then we speak of a reflective program, in which case, of course, object program and language and metaprogram and language coincide. If reflection is limited to what you might call read access, so we only examine the object program, then this is called introspection, and this is the Java situation, and this is the focus for the rest. Okay, let's have a closer look at Java's reflection API. So this API boils down to these classes here, or types. So, and just by the name, it's clear that the API essentially comes in the form of a, if you like, object model for object models. So we have types, class, field, method, constructor, and these are obviously types that, well, are quite able to represent the elements of an object-oriented program. So let's just see how these types show up in our example. So here's the code again, where we kind of look up a class, look up a constructor, look up a method, where we instantiate a class and then invoke a method. So the types class, constructor, and method show up here. So this is how we get access to elements of our Java program. And we use method for name, a static method, to actually translate the string for a class name into the actual class. We use getConstructor to look up the default constructor for a given class. We use newInstance to actually make the constructor perform construction. And we use getMethod to look up a method by name. And we use invoke to invoke an actual method. So a somewhat deeper look at the type java.lang class, which obviously is meant to represent classes, and so it happens also interfaces in a Java app. And since we need to treat argument and result types in methods also in some way, there are actually designated instances of java.lang class for primitive types and also for void. So in this way we can treat all kinds of types in a homogeneous manner. And it's also interesting to know that every object, of course, knows its own class. So we can always have a mapping from object to the class. I mean, in the sense of the reflection API, to the object that represents the class. And each class also knows of its class. So we can also map, we can map classes to the objects that represent the class. All right, so here's the interface. So we basically have many getters. This is like that, so that we can examine classes in all kinds of ways. So what is the name of a class? What are the constructors, the fields, the methods? What interfaces are implemented? What annotations are attached to the class? What's the package of the class? What's the superclass, and so on. And there are no setters, which basically means, yes, we have read-only reflection, so we cannot at runtime change our classes in a program. So here's the next type of the Java Reflection API method for representing methods. And again, we've got access to all the important ingredients of a method, except that we cannot really examine the method body with the Reflection API. Again, we've got lots of getters on an instance of method here, and we've got no setters again because we cannot change the methods or the type of the methods. And in addition, we also have invocation because eventually we want to invoke methods. We always have then to supply the receiver object on which we want to invoke the method. Because remember, these method objects are not associated with particular Java objects. No, they are actually associated with class objects, okay? Likewise, we have an API for fields, so we can retrieve the type of a field, we can change the value of a field, read the value of the field. So we've got a few getters, and this time we've got a setter, but this doesn't mean that we can change the field declaration in any way. I mean, certainly we cannot change the type of a field. We can only change the value of the field. So this is not in conflict with read-only access through reflection. So now let's work through a number of reflection examples to better understand how the Java Reflection API works. Our first example shall be object dumping. So we imagine that given any sort of object graph, we would like to print out the object graph in a nice way so that we use indentation to kind of convey the structure. So in this example here, we assume that we have a simple class tree for binary trees. And if you assume that we construct a binary tree with this sequence here, and then in the end we say dumper dump tree, we would like to see this sort of print out. And again, this should work for sort of arbitrary object graphs. You might think of this as a kind of generic toString functionality, where the programmer doesn't need to provide any type-specific functionality, but rather this dumping functionality just works automatically for pretty much any class. Okay, so let's look at the code. So here's the tree class again, okay, just for playing with object dumping. Here is the demo code again, where we construct some trees and we invoke dump. So let's look at the dump functionality. So obviously we need to deal with indentation. So therefore we basically start with a dump method, with the initial indentation here, and then we will gradually increase indentation, okay? Just to remind you of how we use indentation here, let's just run the demo anyway. So, okay. So this is the kind of output we want to see, right? And this is how we see that there is different indentation applied. Okay, let's go back to the dumper functionality. So what we essentially do here in the dumper loop, we look at a given object, we retrieve its class object, and from that we extract the fields of that object, and we iterate over these fields. So we want to show field by field. We apply the current indentation, and now we look at the value for that field. Okay. We also send the type of the field into the output. And now we examine whether the type of the field is a primitive type. If so, there is guaranteed to be a value which we can just print out, and we don't need to drill any deeper. If it's not a primitive type, it's a reference type, and so it could be null. If it's null, we just say so. Otherwise, what we do is we recurse into the value with an increased indentation. And that's already pretty much all there is, except that we might need to do some exception handling. But that is the introspection-based code for dumping objects. Now let's do another example. So let's suppose we want to compute total over all employee salaries in a deeply nested structure of companies, right? And of course we could write code, type-specific code, where we just go into the company objects. We could use the visitor pattern, we could use other design patterns, and we could just locate all the salaries and total them. But we would like to write less code this time around. That is, we would want to write no type-specific code other than just identifying salaries directly. So we want to use introspection for walking the object C and to find all salaries. Okay? So let's look at this. So we've got some test case here, total test. It reads some company from a file. It totals the salaries in that company. And so let's see how total is programmed. And this is basically all the code we had to write for totaling salaries, which is very little code. What we rely on here is we rely on a worker class, which in turn relies on reflection. And this worker class gives us iterator access to all the objects in a given object C. So by this loop here, we are able to see every sub-object of an initial object C. And then we just need to perform type test to see whether this is maybe an employee object. And if so, we can just extract the salary and add it to the result variable. So this is all the code, all the type-specific code we had to write. And now let's just look at the worker implementation, which of course relies on reflection. While the worker class, of course, implements iterable objects so that it can provide iterator access to all the objects in a given object. The constructor just receives some object and then uses a local method to really walk that object and to collect all the objects encountered in a list. So how does this walk look like? Well, we have to distinguish a number of cases, but this object could be a list object, and if so, of course, all the elements in the list should be added to the list of sub-objects, and we also need to walk each and every of these elements in the list. If it's not a list, then it's some other kind of object, and then what we do here is we go and find all the methods, and we try to filter out the methods that look like getters. So if it's a getter, well, then we invoke the getter, and whatever we receive back, we also add to the list of objects the worker provides. And of course, we also drill deeper into this object that we obtain as a result of the getter invocation. Again, there's some exception handling, but that's pretty much it. And then we just implement the iterator method so that client of the worker class can actually access the list of objects that have been set up here. Okay. So now let's just face an interesting tiny challenge. Just to better understand some of the characteristics of Java's reflection. So a reasonable question to ask to a reflection API would be, given the class, please provide me with all the subclasses of it. It turns out this question is not supported by Java's reflection API, so we cannot just retrieve the subclasses of a given class. What we can do is we can ask for the superclass of a given class, but we cannot simply obtain all the subclasses of a class. So why is that? Oh, there's a good reason for why we cannot ask that question. It's because it's not easy for the Java runtime to know which classes or subclasses of a given class. Of course, on the grounds of all the classes the Java runtime has seen up to a given point, it may be able to tell what subclasses it already knows. But that's not quite satisfactory, because it might be that there are much more subclasses around. It just so happens that they have not been loaded yet because no reference has happened yet to them. So then we could only hope that the Java runtime would somehow try to locate all the subclasses in the Java path so that it could answer this question. But this would be quite expensive. It would essentially boil down to loading all possible classes that are reachable through the class path, which is maybe not a good idea. So this shows you that we have in Java some sort of interaction between class paths and what reflection can do. So here's a related problem. So let's try to basically find all the classes in a package. I mean, it's not quite the same thing as the one before, but it's a nice simple problem, finding all the classes in a package. And we also need to interact with the class path here or with the file system. So what we do is we pass a package as an argument, and we expect to get back a list of class objects. And then what we do is we take the package name and we manipulate it so that it becomes sort of a file name. Okay. And then we iterate over the directory listing to find all .class files. So the assumption we make here is that a package name translates into a standardized location in the file system. This is obviously not necessarily true in all cases. And so then once we find such .class files, we extract the class name from it. We requalify it by adding the package name to it, and then we ask Java Reflection to possibly load that class. And the assumption here is that class loading sort of looks into the same location, and that we also have looked into the right location in the first place. And this way we get a class object, we add it to the list, and we will return it. Okay, so this is a nice example of how reflection and class paths and file system cooperate in such a scenario. Okay, one more topic, topic of metadata. So we understand by now what metaprograms are. Well, these are programs that generate, analyze, or control other programs. And actually in computer science, metadata has lots of meanings. Well, they are all sort of related, but we take a narrow view here on metadata. That is how it's used, how it's understood in the context of metaprogramming. And then metadata is essentially data that is attached to programs to control metaprograms. So in Java, actually, we speak of annotations. Okay? And we all are quite familiar with metadata. So for example, here we see some piece of code, a method that is annotated with the test annotation. And of course, what is meant by this is that JUnit could find this annotation through reflection and then would be instructed to execute this method again through reflection. Okay. So annotations can be associated with methods, as we just have seen, but also with fields and with classes. In fact, they can also be associated with declarations of annotations, as we see. So annotations don't directly change the semantics of a program or a method, but they control metaprograms in how they interpret some given piece of code. Okay, so we have seen the JUnit scenario. Annotations are used a lot. I mean, many frameworks rely on annotations. So for example, serialization and object relational mapping and such frameworks, they use annotations to control their persistence or serialization story. So here's a more complex example of an annotation in which we also see that annotations can contain additional data. I mean, not just like the test annotation, which was just a tag essentially. So here we have an annotation request for enhancement, and there are components for the ID of this request, and there's a synopsis, a summary, and an assigned engineer, and also a date by which we want this enhancement to be implemented. And again, this annotation is assigned to a method, travel through time. Annotations need to be declared. I mean, I cannot just start using arbitrary tags. No, I mean, each annotation basically also requires a corresponding annotation declaration. So here we have the declaration for our request for enhancement. So we see that annotation declarations take the form of special interface declarations. That's how Java does it. So we have to have an @ sign here, interface, and that's how we introduce an annotation. And then the components of the annotations, if any, they are essentially methods without arguments. And then we should also understand that we cannot use arbitrary types here for the components. In particular, we cannot use arbitrary reference types here because metadata is essentially data, and so we don't want to get into the business of serializing objects or something like that. So here's the summary of the rules for annotations declarations. As I said, it's a special interface declaration form starting with the @ sign. We use method declarations without parameters, without throw clauses, and we can only use primitive types, string class, enum, and array types for the components of an annotation. We can, as we were also seeing, we can associate a default to each method, like unassigned. When we declare annotations, we might also annotate those declarations, and obviously these things would need to be called meta-annotations. So what we see here is the meta-annotations that go to a JUnit-like test annotation. So let's just understand this in detail. So we declare an annotation test, just like in JUnit, even though in JUnit we would have some component here, but okay, it's a simplified test declaration. And then we annotate this annotation declaration by retention policy runtime, and target element type method. These meta-annotations basically control how these annotations, the test annotations, are used. So retention policy runtime means that test annotations remain at runtime. So they are not stripped off by compilation. They will go into the Java bytecode essentially. So we need this here for JUnit like test because, I mean, obviously JUnit is executed at runtime. It needs to see what methods are annotated with the test tag. There are other scenarios where only the IDE needs to look at the program and then the runtime retention policy is not necessary. And by the other meta-annotation element type method, we just point out that the test tag should only be applied to methods and not to classes or fields. In this manner, we restrict how we can use the test annotation, and we prevent users from using the annotation in the wrong way. Okay, so then we have all the tools to actually implement some small subset of JUnit as a metaprogram, I mean by means of introspection, while relying on annotations. So what we are going to do is we are going to write a tool which takes a class name as an argument, as a string argument. We are going to use introspection to find all the test methods in the given class. We execute them and we keep a record of success and failure. So this is the class on which we are going to perform tests. Well, this class actually holds 3 methods, M1, M2, M3. Only M1 and M3 are tagged as test methods, so M2 is not really a test method. So if you were to execute M1, this would obviously go without problems, whereas here M3 is going to throw an exception. So we should expect to see one test to pass and one test to fail. Okay, now let's look at this test declaration. I mean, we have seen it before, but it's here. It's not like the normal JUnit test annotation. No, it relies on our own declaration. So we have a test annotation, retention policy runtime, target element type method. And that's the one we use on M1 and M3. Let's just run the test and then we understand how the framework works. What we do here is we invoke our tool and we pass this class name as an argument. So if you do this, we see that one test passed and one test failed, and we even see that some invocation threw an exception. So now it's time to understand the actual run test functionality. This is the code that mimics JUnit, and as you can see, it's quite concise. So it's a main method. We receive the class with the test methods as a name. We use 2 variables here, passed and failed. So we iterate over all the methods of the given class. We check whether the given method is annotated with test. If so, we try to invoke the method, and we slightly deviate from JUnit here. So JUnit assumes that we have instance methods. For simplicity, we just assume that we use static methods here. Therefore, we can just pass null as the receiver object. So if the invocation goes through, we can increase the passed counter. If we end up in the catch here, then it means that the invocation failed, and so we have to increase the fail counter. Once we have seen all the methods, we just communicate the summary, and that's it. So we could quite easily simulate a good deal of the JUnit framework by using our own annotations and our own piece of code for relying on introspection. So that's pretty much it I wanted to show you here. I mean, there's of course much more to be talked about with regard to metaprogramming. For example, we might want to also somehow examine and maybe even modify the method bodies of Java methods. Then we could use the bytecode engineering frameworks such as ASM, and they could even be combined with class loading in Java, so we could actually to some extent go beyond introspection. Now, the kind of reflective code that I've shown you using the classes class, method, field, constructor, using a lot of strings, is obviously quite generically typed, and so there's many programming errors conceivable. And that's also true when you start to use something like ASM for bytecode engineering. So there's something called aspect-oriented programming, and for Java there's also a great extension called aspect-J, which sort of supports many of the scenarios where you otherwise would use reflection for, but in a much more high-level and typeful fashion. If you are not restricting yourself to reflection in Java, but you somehow want to consume Java programs offline, then you of course need a parser, and for example the Java parser technology is one option that comes to mind. Pretty much any modern programming language has support for reflection, well, and in some cases in fact really proper reflection and not just introspection. And I'm just referring to one example here. That's how Python supports reflection. That's it. Thanks.